This presentation was previously given by Dr. Michael Schultz and Dr. Florian Bell of Grace Biolabs at the 2013 Microarray World Congress. All information contained in this presentation is copywritten by Grace Biolabs 2013, all rights reserved. Today we will be discussing a protein microarray platform centered on the use of porous nitrocellulose film slides. Nitrocellulose offers significant advantages for numerous protein array applications, and today we will discuss the advantages of using this binding surface compared to other popular microarray surfaces. Subsequently, we will also introduce you to an alternate approach for labeling and imaging protein arrays, which work synergistically with the properties of porous nitrocellulose. Grace Biolabs invented the methods for producing thin-film nitrocellulose slides in the mid-'80s. ONCYTE slides have become the surface of choice for many protein microarray applications, a great example being reverse-phase protein arrays. Now, for simplicity in today's discussion, we will refer to porous nitrocellulose film slides as ONCYTE PNC. Primarily, there are three types of protein microarrays, and there are many microarray binding surfaces available on the market. Many of them are adequate for one application or another. Today, we will show you why ONCYTE PNC is the surface of choice for all of these applications. First, let's take a moment to describe ONCYTE PNC. There are many types of nitrocellulose on the market, but they differ quite substantially. For example, membranes for Western blotting and diagnostic strips have nitrocellulose formulations designed for those specific applications. They both are thick membranes, but differ in their binding capacities, porosity, and wetting characteristics. ONCYTE PNC slides are very different from these. This is a specialized formulation for use as a microarray binding surface. Unlike transfer and lateral flow membranes, ONCYTE PNC is much thinner, and the porosity has been optimized to give controlled wetting and very high binding capacity. When expressing protein binding per unit volume rather than unit area, you can see that ONCYTE PNC actually has the highest binding capacity of these membrane types. This is a function of ONCYTE PNC's porosity. For comparison, here are SEM images of an ONCYTE PNC film and a lateral flow film. Many of the pore sizes may appear to be the same on both images, but please note the magnification differences. The entire structure of the ONCYTE PNC shown here would fit inside one pore of the lateral flow film. The smaller, closed pore of ONCYTE PNC supplies a large surface area which contributes to its high binding capacity, while the larger open pore structure of the lateral flow film is designed for more rapid fluid transfer through the film. In addition, the formulation and pore structure promotes more controlled, uniform wetting, better suited for microarray deposition. The fluid dynamics of ONCYTE PNC was recently modeled by a group in the Netherlands. The data demonstrate the desirable wetting and binding characteristics created by this film's pore structure. The investigators found ONCYTE PNC to distribute spotted protein evenly on the spotted surface and into the film with excellent vertical flow while limiting horizontal flow, perfect for higher density microarrays. More importantly, the surface of film slides is ideal for protein binding. It provides an irregular binding surface with many crevices and grooves where proteins can situate themselves, and the method by which it binds is non-covalent. Both of these characteristics provide an ideal environment for the preservation of proteins' three-dimensional tertiary structure and function. Due to these various characteristics, ONCYTE PNC outperforms other commonly used protein array surfaces, including hydrogels and functionalized glass. ONCYTE PNC has 500 times the protein binding capacity of these other surfaces. This can extend the linear dynamic range of functional assays nearly 100-fold. Additionally, we observe much better sensitivity with ONCYTE PNC, with a 50-fold lower limit of detection. These gains in performance are primarily due to the high binding capacity of ONCYTE PNC and the retention of protein structure. There is another phenomenon we call resonance scattering amplification, which is inherent to porous film. The result of our assay is literally a built-in signal amplification method for enhanced detection. We will describe how this occurs in more detail in the latter portion of this talk and how we are using it to optimize detection strategies with porous film. All of these performance advantages make ONCYTE PNC ideal for many protein array applications where binding sensitivity and specificity are desired. The high binding capacity of ONCYTE PNC translates to a significantly higher sensitivity for reverse phase protein arrays. When compared to other binding surfaces, ONCYTE PNC provides 10 times the sensitivity. This sensitivity is critical for many researchers who routinely use minute tissue lysates from tumors and are looking for subtle shifts in protein phosphorylation states. This performance has made PNC films the surface of choice for RPPAs. Their use is growing rapidly in cancer research and drug discovery, and this technology has been validated for use in clinical trials. In addition to the high binding capacity, the ability of ONCYTE PNC to preserve antigenicity makes it ideal for antigen capture assays. ONCYTE PNC performs significantly better than any of these other microarray surfaces in functional capture assay. The improved signal-to-noise in this cytokine assay resulted in a 10-fold lower limit of detection over any of these other substrates. Whole proteome serology screening is a perfect example of an antigen capture assay where ONCYTE PNC is utilized extensively. Researchers at UC Irvine are doing some exciting research by screening whole pathogen proteomes for profiling of pathogen infection, the identification of biomarkers of infection, and the identification of whole drug targets for more effective treatments of infection. ELISA-type sandwich assays have been slower to transition into the microarray format, and many of the ones that have are primarily using functionalized glass surfaces. We've found that many users evaluating the performance of ONCYTE PNC with sandwich assays are using methods and reagents suited for glass surfaces, and which actually work against the benefits of PNC. One has to recognize that ONCYTE PNC requires methods and reagents that are more suited to this specialized surface. With many of the methods being implemented, these ELISA-type assays were resulting in high intra-assay CVs and very high backgrounds. Researchers at Grace have taken great care to formulate reagents and develop methods for spotting, preserving spotted protein, and blocking ONCYTE PNC to maximize its advantages. In the next few slides, we will show you that by optimizing these conditions, ONCYTE PNC proves to be an exceptional performer for sandwich assays. Here are two examples of how to improve antibody capture assays with ONCYTE PNC by optimizing spotting conditions. In many instances, the high binding capacity of this film is not being used effectively. Typical spotting concentrations for antibody arrays on glass slides are marked with the X around 0.1 milligrams per mil. As shown with IL-1 alpha, with ONCYTE PNC, you can spot 10-fold more capture antibody and achieve nearly 10-fold higher signal-to-noise. Additionally, choice of spotting buffer can play a critical role in effective protein binding and optimal spot morphology. Here are comparative spotting results between an optimized spotting buffer and standard phosphate buffer. You can see for proteins like interferon gamma, protein aggregation is minimized and optimal spot morphology achieved. What happens after spotting is just as important as the parameters during spotting. This is a critical stage in the life of a microarray, where proteins are subjected to an unnatural, dry state, and then expected to rehydrate and perform optimally. It's no surprise that many proteins do not perform optimally. This is an example where we have monitored spotted cytokine antigenicity over time, and with and without protein preservation reagent. Without effective preservation, 75% of the spotted cytokines lost antigenicity in less than 200 days. With our preservation buffer, we retain 100% antigenicity over the course of a year. Finally, One of ONCYTE PNC's greatest advantages can be its Achilles heel if this surface is not effectively blocked during the assay. Of course, this is true for all reactive binding surfaces, but especially true for PNC due to its much higher binding capacity. Many microarray users who have tried PNC have seen results similar to what you see here with just plain PBST blocking. You get higher backgrounds and inverted spots where the spotting material actually blocked better than the blocker itself. As you can see here, effective blocking can prevent this and give much lower background. In fact, many common blockers do not effectively block PNC. Take the milk protein casein, which is an effective blocker for Western blots. It actually results in increased backgrounds along with various other protein-based blockers. With assay optimization, ONCYTE PNC is an exceptional surface for ELISA-type sandwich assays. We assessed multiplex sandwich assays on PNC for various cytokines, and here the performance of IL-6 and IL-1 alpha. The areas highlighted in blue are the specs for these ELISA antibody pairs in standard microtiter plate assays. The dynamic range of these assays are typically no more than 2 orders of magnitude, with limits of detection from 2 to 5 picograms per mil. This is using standard methods with signal amplification. Using these same ELISA antibody pairs on ONCYTE PNC improves dynamic range and sensitivity. The linear dynamic range of these assays on PNC is 3 to 4 orders of magnitude, nearly double the microplate assay. The limit of detection was in the low to sub-picogram per mil levels, and I have to emphasize this was achieved with no signal amplification. ONCYTE PNC indeed provides an ideal surface for protein microarrays, and we've shown some of the exceptional results you can obtain with these surfaces. In this half of the presentation, we will focus on the practical applications of PNC when used as a surface for immunoassays labeled for fluorescent imaging. Fluorescence as a label for immunoassays is widely used because of its high sensitivity, a large dynamic range, and its relative ease of use compared to colorimetric and chemiluminescent detection. Remarkably, fluorescent emission is much brighter on PNC surfaces compared to glass. Let's see if we can understand why by examining the geometry of the film and surface and how it affects our ability to detect fluorescence. Why are PNC films white? Porous nitrocellulose films are white because the film reflects room light in a diffuse pattern known as Tyndall scattering, a process in which light is scattered by randomly shaped features whose size scale is about the same as the wavelength of visible light. It does not matter whether the features are convex, as with tiny particles, or whether the features are concave, as with voids in the film. The outcome is the same. Scattering amplitude varies both with the wavelength of incident light and with the size of the scattering centers. It is the very nature of this scattering that we can exploit when we perform our assays on PNC relative to clear films or glass. Consider a fluorescence assay prepared on a clear film surface and measured with a digitizing scanner. When excitation light strikes the clear film imbibed with the fluorophore label, some of the light is incident on the film surface where there is no label and passes through the film, unable to excite fluorophores. When photons do strike the fluorophore, they are absorbed and emit fluorescent light, but only the light which is emitted back toward the direction of the detector is measured. All of the light that is focused on the surface, only a tiny amount excites fluorescence, and of the emitted light, only a tiny amount is captured by the detector. This means that the digitizing scanner has to have extremely sensitive electronics to detect the signal. Now consider a fluorescence assay prepared on PNC. Where excitation light strikes the surface of the PNC, tiny voids in the film scatter the incident light, causing many of the photons to reflect back onto fluorophores, thus increasing the probability that the excitation light will be absorbed by a fluorophore. Thus, the effective extinction coefficient is greatly increased. In addition to this effect, fluorescent light that is emitted into more obtuse angles can be reflected by the PNC surface back toward the detector, also increasing the total amount of capture emission light. Again, the signal is increased many times. Classical scattering theory tells us a resonance condition develops when the wavelength of light is a certain value compared to the size of the pores. From SEM imaging, we can measure the distribution of the pore sizes in PNC. From this, we can predict the resonant wavelengths. Here, we see the amplification effect of resonance for one of the more prevalent pore sizes. This resonance increases the amplification, especially when the wavelength approaches 700 to 800 nanometers. We can illustrate the amplification effect by comparing similarly prepared arrays tagged with fluorescent labels on both PNC and epoxy-coated glass. In the case of PNC, the signal strength is much greater, by a factor of 150 compared to the clear film. We can additionally demonstrate the unique ability of PNC to amplify fluorescent signals relative to non-porous film by a simple experiment. We first make a film of PNC and create an assay containing a fluorescent label. We scan our film and record the resulting signal. Then we collapse the film pores using an organic solvent that does not break or remove the polymer chains. Following the collapse, we rescan our film using identical settings. This slide shows the results wherein the signal has been reduced by a factor of 10x in the collapsed film. Earlier, we compared the brightness of an assay on several different films. The large offset between the PNC film results and the glass results illustrates the large gain provided by pore-enhanced resonant scattering. Let's turn our attention now to organic fluorophores used as immunoassay labels. Fluorophores are efficient emitters because they are organic molecules containing double bonds that absorb visible light, give off part of the energy in the form of heat, and re-emit a Stokes-shifted photon. Thus, the absorption band and emission band are separated by a very small difference in wavelength domain. In fact, nitrocellulose also has a double bond, so one would expect that nitrocellulose has an inherent native fluorescence, and it does. When PNC is used as a film for microarray assays utilizing visible light fluorophore markers, the native background fluorescence is easily detected. This background is generally referred to as autofluorescence and leads to a practical lower limit of detection. Now this limit is only realized at extremely low levels on glass surfaces, so from this perspective, glass should be a preferred surface and generally is. Our investigations have demonstrated that the native fluorescence of PNC is a strong function of wavelength and decreases rapidly toward the near-infrared. At 700 nanometers, the native fluorescence is about 2x that of glass, but at 800 nanometers, it drops down to the same level as glass. Important to note here is that when you move into the near IR with the label wavelength, you get increased scattering due to the resonance effect, and you get less autofluorescence. However, if you reduce the wavelength into the visible, both phenomena work against you. It makes sense that if we can, we should label our PNC assays with a near-infrared fluorophore rather than a visible light fluorophore. In fact, digitizing scanners are now becoming available that do operate in the near IR, and in our experience, they provide superior performance to visible light scanners. We were particularly interested in knowing how much of the signal to background would be improved as we varied the label wavelength. We prepared similar assays using 635, 680, and 800 nanometer organic dyes and set up the scanning parameters so that we obtained nearly equal signal strength in each case. Evaluating the background, we saw that it decreases significantly as the wavelength increases. This led to an improvement of almost 4x in the signal to background as the wavelength varied from visible to near IR. Why would anyone not use PNC as an assay surface in the near IR and get 150 times increase in brightness and essentially the same background as glass? Organic fluorophores are widely used as labels for microarray assays because they are relatively inexpensive, widely available, and their use is well established in the literature. Despite these advantages, organic fluorophores do have practical drawbacks. First, in order to detect the emitted light from a fluorophore, you need a very intense excitation laser, extremely good optics, and a highly sensitive detection system. Put all this together, and you typically have a digitizing scanner that can cost as much as $100,000 and weigh about 50 kilos. Second, organic fluorophores have a decay mechanism known as bleaching. Fluorophores that are repeatedly scanned with a high-power laser undergo a significant reduction in brightness because the double bonds are being broken by the intense radiation and therefore cannot contribute to fluorescence. Third, as we've seen earlier, there is an overlap of the excitation band with the emission band. Light that is emitted as fluorescence can be reabsorbed by the dye, leading to an upper limit on the brightness of the dye. This saturating effect is known as quenching and limits the ultimate sensitivity of the assay. Fourth, when organic dye-labeled immunoassays are exposed to ozone, the dyes can become quickly broken down, again reducing the brightness of the dye and limiting our ability to detect it. How can we surmount these disadvantages? We must find a different fluorescent species that doesn't require so much stimulation light, the same as saying that it would have a much higher extinction coefficient, one that doesn't bleach, doesn't quench, and isn't prone to ozone degradation. There are other interesting alternatives to organic fluorophores, for example, quantum nanoparticles and tandem dyes. In this talk, we will focus our attention on nanoparticles. A quantum nanoparticle, QNP, is a fluorescent inorganic crystal capable of absorbing light over a range of wavelengths while emitting light in a very narrow band. QNPs can be obtained commercially as conjugated labels bound to antibody and streptavidin molecules. In this cartoon, we see a QNP bonded to several streptavidin molecules. Typically, 5 to 10 streptavidins can attach to a single QNP. Here we can get a feel for the relative size of the PNC film pores and the QNP size and a representative antibody-protein conjugate chain. Optically, the center of the QNP emission band is weakly related to the size of the nanocrystal itself, thus enabling the emission band to be tuned over a wide range of wavelengths while maintaining a narrow line width. This provides for a spectrum of available quantum nanoparticles whose emission peak can be matched to many of the organic fluorophore wavelengths. Right away, we can observe several advantages of QNPs used as fluorescent labels. First, because the emission bands of the QNPs are very narrow and their excitation band is in the ultraviolet, we can use a much wider emission filter to gather more light than we could with an organic fluorophore. This already gives us an improvement in brightness of the label. Second, the narrow emission bands open the possibility to wavelength multiplex various labels onto specific proteins or antibodies within the same assay well. This represents a new type and a greater level of multiplexing than has been generally practiced. An important third point is that an excitation laser of a particular wavelength is capable of producing fluorescence in a series of quantum nanoparticles. So if we are only using QNPs as labels, we could use a single excitation laser, thereby reducing the cost of the instrumentation. The table included in this slide contrasts the characteristics of conventional fluorophores and QNPs. A very important point here is that QNPs, when stimulated with ideal excitation sources, are as much as 20 times brighter than organic fluorophores, the same as saying the extinction coefficient is 20 times greater. Earlier, we mentioned that quantum nanoparticles should not exhibit quenching because of the small overlap of absorption and emission bands. We have experimented with quantum nanoparticles in our laboratory and have verified that by scanning of spotted labels using an ultraviolet laser source, the emission continues to increase with stimulation light intensity up to 1 watt per centimeter squared. In addition, we have not noticed any measurable bleaching effects with repeated scanning. Despite that digital scanning is a very sensitive, high-resolution technique, it is unfortunately an inherently slow process because each individual pixel in the scan must be obtained independently and sequentially. Scanning a single microscope slide can take as much as 3 minutes to complete, and commercially available digitizing scanners that are configured to scan a large array cluster, such as a 96-well microtiter plate, require many minutes to complete a full scan. At Grace Bio Labs, we have developed a new type of microarray scanner that could take advantage of the amplification property of PNC, utilize the brightness of QNPs, and at the same time reduce the high cost of the instrumentation. Our work in developing a new generation of array scanners has been based on the use of imaging as opposed to digital scanning. In digital imaging, a large area or slide or plate can be imaged at once in only a few seconds. So if imaging could be made as sensitive as digital scanning, then it would have advantages. We have determined that digital imaging can be made as sensitive to dilute protein antibody assays as digital scanning with organic fluorophores, provided certain design features are integrated into the imaging system. Earlier, we spoke about the virtues of using optimized spotting buffers and blocking buffers to take full advantage of PNC as an assay surface. We started with this foundation and then introduced QNPs as labels in the assay. Because of its amplification properties, PNC provides the additional signal strength that is needed for sensitivity in the imaging process. Finally, we maximize the advantages of speed by designing the instrument to capture a large area of the slide in one image, greatly reducing the measurement time. Our design concept is called ArrayCAM. The optical configuration of our imager is similar to many used for imaging applications in the life sciences. A dichroic mirror is used to direct the stimulation light onto the surface of the array, where it excites the QNPs used as labels. The scattering properties of the PNC amplify both the incoming light and the fluorescent light. Amplified light then propagates through the dichroic mirror toward the camera lens and imaging chip. We use an extremely bright diode laser whose wavelength is less than 425 nanometers, ideal for excitation of the QNPs. The camera system is based on modern CMOS imaging chips, whose pixel density provides a resolution at the target of about 10 microns, sufficient for the vast majority of even very dense microarrays. In contrast to digital scanning, our imaging times are much less, about 30 seconds for a full slide and about 4 minutes for a 96-well plate. Because images are obtained quickly, the operator is free to make adjustments in acquisition parameters and re-image, thus obviating the need for pre-scans. Because the design of an imager uses low-cost components compared to a digitizing scanner, the eventual price point of imagers can be much lower as well, reducing the barrier to entry for small labs and enabling point-of-use practices for microarray imaging and analysis. To illustrate the performance of the ArrayCAM, here are data from an antibody detection assay labeled with both near-IR 800 dye and an 800 nanometer QNP, and measured with a near-IR digitizing scanner and ArrayCAM. A threshold of signal to background greater than 2 was used for discrimination of positives. Good concordance results over most of the dynamic range, the ArrayCAM having somewhat better detectivity at lower signal-to-noise levels. Here are some examples of additional applications of imaging with PNC microarrays. In parallel with the hardware and optics development of the ArrayCAM, we have also been validating its use with existing array protocols using QNPs, other organic fluors in various microarray formats. For example, we've taken existing RPPA methods and used QNPs instead of standard fluors. We see the same expected selectivity and sensitivity for various cancer biomarkers with these assays. With ArrayCAM, we see comparable signal intensities and assay dynamic range as with standard microarray scanning. This was accomplished with ArrayCAM at a fraction of the price and time for conventional scanning. Using ArrayCAM, we've improved sensitivity, assay time, and detection time by converting from a colorimetric method to a fluorescent method. Here is an example showing excellent discrimination between two serum samples using this autoimmune antigen panel. ArrayCAM imaging resulted in higher sensitivity with QNP fluorescence than with the colorimetric method and didn't require any enzymatic signal amplification. Additionally, this image was acquired on ArrayCAM in about 2 seconds, further reducing total assay time. We are developing methods with ArrayCAM and near-IR detection to further lower the limit of detection of sandwich assays using PNC films. Currently, compared to what we showed earlier in this talk for IL-1 alpha, we've lowered the limit of detection by 1 order of magnitude into the sub-picogram per mil levels. As mentioned earlier, ArrayCAM is also capable of detecting other fluors, and we have developed methods for some commonly used applications. An example of this is total protein staining with cyproRuby, which is routinely used with RPPA methods. Protein detection on ArrayCAM shows excellent linearity and accurate protein quantitation with very low CVs. The optics on ArrayCAM can be used for multi-mode detection. Here is an example where identical RPPAs were performed with either fluorescence or colorimetric endpoints and imaged sequentially on the ArrayCAM in 2 functional modes. In this particular case, an 8-plex biomarker panel was assayed in duplicate on 16-pad PNC slides. ArrayCAM provides the ability to excite multiple QMPs with 1 excitation wavelength, opening the capability for multiplexing assays on single arrays. Here is an example of a multiplexed RPPA in a single well for the detection of a phosphorylated cancer biomarker. The phospho-AKT was detected in the 655 nanometer emission wavelength, while simultaneously detecting the non-phosphorylated AKT using the 800 nanometer emission wavelength. Use of QMPs allows for even higher levels of multiplexing, and we are currently developing methods for 4-plex assays. For the ultimate in multiplexing, many assays will be converted to a 96-pad or well microtiter plate format. We have a version of ArrayCAM which can accommodate imaging in this format, and here is an example of an image of a 96-pad ONCYTE PNC showing 95 distinct subarrays and an identification barcode. The data clearly show that ONCYTE PNC is the surface of choice for protein microarrays. We've shown that its many attributes make it ideal, not only for reverse phase protein arrays, but also for antigen capture arrays and antibody capture arrays. The reagents designed for PNC and the optimized detection strategy form a platform which works synergistically to maximize all of the benefits from this surface. We at Grace Biolabs invite collaboration and welcome the opportunity to discuss your applications and how we can incorporate ONCYTE PNC and ArrayCAM into your workflow. We'd like to thank you for your attention.